test the sound, please?
Yes.
Ah, perfect. Can you do the solo neo anyway?
Sorry?
Okay. So Fabio has been sick at least, doesn't look very sick anymore. We're happy to see you. Anyway, we have decided to just record the talk. It's 6 minutes sharp. 6 minutes minus, I don't know, 8 seconds. So let's go for this.
And I'm a PhD student in Daniel Olifle's group. I had the terrific timing of getting sick just before dynamic walking, so unfortunately I cannot be there with you today. However, Yannis was so nice to help me present remotely, and so in this talk I will give you an overview of my latest results on biological damping. But what do I mean with biological damping? We know that muscles are compliant actuators, which means they possess intrinsic mechanics. And these intrinsic mechanics allow muscles to react instantly to external perturbations, a capacity that takes the name of reflex. One particular mechanical property of muscles is the force-velocity relation, which describes a nonlinear dependence between the muscle fiber force and the muscle fiber velocity. It is argued that the force-velocity relation provides some form of physical viscous damping to the muscle fibers, which would be a very convenient feature during fast locomotion. For example, if we consider running, we know that the nervous system struggles to reject sudden step-down perturbations because of intrinsic neurotransmission delays. However, when the new impact condition increases the muscle fiber velocity, the force-velocity relation will instantly adjust the muscle fiber force, and this sort of damping response will buy precious time for the nervous system to react. A problem with this biological damping hypothesis is that it is difficult to test, and this is because it is difficult to extrapolate the amount of force produced by the force-velocity relation from the highly nonlinear dynamics of muscle contraction. So we tackled this issue by developing a mathematical algorithm that, starting from the classical formulation of hill-type muscle models, makes the force contribution of the force-velocity relation explicit. We then tested the damping hypothesis from the literature by applying our novel formulation to the mechanical analysis of a vertical hopper, employing different levels of step-up and step-down perturbations. In particular, we measured whether the touchdown force and the energy dissipated by the muscle fibers during preflex increased with higher dropping heights, and to what extent this adjustment was driven by the force-velocity relation. For our analysis, we also compared two different stimulation strategies. This was necessary because the shape of the force-velocity relation depends on the level of excitation of the muscle. In preflex constant, the muscle fibers receive a constant stimulation during the whole preflex. Here, motion regulation could only occur because of the muscle's passive mechanics. In preflex rising, we sent a feed-forward stimulation to the muscle fibers, which was fixed in time. This means that any change in touchdown timing will have produced a different muscle excitation level at touchdown. Our results show that in preflex constant, the muscle fibers could adjust the touchdown force to the different perturbation levels, and this adjustment was driven by the force-velocity relation. However, the force-velocity relation was the least contributing factor in regulating the dissipated energy during preflex. On the other hand, the open-loop stimulation allowed the force-velocity relation to produce considerably more effective regulation of both touchdown force and dissipated energy. To understand these results, we need to take a look at the flattening side of the force-velocity relation and its tunability. With a constant stimulation, the shape of the force-velocity relation stays the same during preflex. This means that as the muscle fiber velocity increases, the force-velocity relation adjusts less the muscle fiber force. With the open-loop stimulation, the shape of the force-velocity relation scales vertically during preflex, and this effect mitigates the flattening side. The effect of this mechanism is that if we look at the force trajectories produced by the force-velocity relation during preflex, in preflex constant we observe very similar trajectories, while much more variety is possible with open-loop stimulation. This mechanism was also previously mentioned in a study that tested muscles' capacity in rejecting sudden changes in ground stiffness. It is important to mention that the flattening mechanism that I just described is an intuitive description of why the force velocity relation benefits from open loop simulation, and a much more detailed analysis is available in our latest publication. Also, because of the high nonlinearity of muscle dynamics, several other aspects can influence our results, making generalizability difficult. For this reason, at the moment we are testing additional hopping conditions to try to understand how they impact our study. So far we explored the influence of the operative side of the force-velocity relation at touchdown and of different element compliance. So far we found that both scenarios support our previous analysis. Our eventual goal is to extend the whole analysis to a complex musculoskeletal model running over rough terrain, so ideally to have muscle trajectories that are as close as possible to biology. I would like to conclude my talk with two take-home messages. First, our study suggests that the force-velocity relation can produce some form of physical damping, but it requires open-loop control to have maximum effect. And second, our study indirectly suggests that tunable physical damping might be a very effective strategy in biorobotic design to achieve robust, fast locomotion with minimal control and no sensing. I would like to thank you so much for your attention, and I hope you're having a great time in Munich. I cannot hear anything. Oh, now I can. I look funny. Can you see me?
Yes. Izzi Fabio.
Everybody. Oh.
Okay, questions?
I'll just shout it out. Okay. It seems like you've done. It sounds like you've done a reformulation of the Hill model that didn't change the model.
Do you hear anything?
I'm not so good
Can
actually.
the speaker come to the front, please? The audience?
Hi. It sounds like you've done a reformulation of the Hill model without changing the model itself in order to deduce these effects. And so I'm wondering if you can articulate a little bit your vision for how reformulating might ultimately change consequences in terms of running optimizations or making decisions based on the long-term consequences of your model.
Yeah, it's a very good question. So yes, indeed, it's a reformulation of a classical time model, and you can apply the algorithm to any other time model, so any form of algebraic formulation of muscle contraction dynamics. I think the main implication is the numerical error that comes with the numerical integration itself. So up to basically computing the partial derivatives, we can do this algebraically because we have the mathematical interpretation that describes the nonlinear function. But then we needed to integrate the integrals in a numerical form. So if you want to study very long simulation, you might get more numerical errors. However, what we did was to test everything offline. So we ran the simulation, we took the data set, and then we ran the algorithm offline. We expect that if you implement the algorithm online in Simulink, it's possible that the solver will also take into account the accuracy of the algorithm. This can maybe provide a more reliable solution for longer durations. But it's something that we didn't test yet, so it's something that needs to be checked.
Antonis?
Okay, my question is if... Okay. Do you think that you could kind of confirm your results by using EMGs and ultrasound in real conditions and actually use the setup that you have in a perturbed locomotion and then confirm what you found? Thank you.
For a second. Sorry.
Like there was some English when it was
Just give me a second. Can you try audio once again? Say something?
Can you hear me?
Yes.
Right now.
Yes.
I just needed a clarification for the previous question because I'm not sure if I got it right. So when you mean validating the data, do you mean in general the results of how the first velocity relation contributes or the stimulation sent to the muscles?
You found that there is some kind of reflex and that there is some change in how the muscle would react after perturbation. So my question is if you could find the same thing and you could confirm that by using an experiment in real humans in the future.
I see. It's a tricky question. I don't know. I would say it's probably very difficult to do this in vivo because somehow you need to be able to isolate the viscous-like response of the muscle, and I'm not sure it is possible to do this with online measurements if there is an instrument that can just check the sort of viscosity that the muscle have. Because when you measure in general EMG and then the muscle response, maybe you get the net outcome of the muscle and the muscle can emulate. And there is also like elastic effect there and many other things going on. So I would say it is probably very challenging to do this in vivo. You can do this in vitro. You can actually sort of muscle contraction experiments, and Matthew Ratz will be on top more about this, so stay tuned for tomorrow. But I would say, yeah, I mean, like running experiments with people, I guess you would be a little bit unethical to test this online, right?
Okay, thank you very much.
We can take one more question if you want. Otherwise, mine. Fabio, thanks for being here. Being with us.